Hello, everyone. Depending on where you're joining us from today, good morning, good afternoon, or good evening. We're happy to have participants from all around the globe joining us today for our webinar, Characterization of Microplastics, Nanotubes, and 2D Materials, presented by Dr. Rob McCuskey. My name is Jared Lepkowski, and I'm the International Sales Manager for the DeLong Instruments Low Voltage Electron Microscopes. I'm joining you today from our North American offices in Montreal, Canada. DeLong Instruments is proud to be sponsoring this webinar today. We hope that you find it informative. Before we get going, I would give an incredibly brief introduction to our company, DeLong Instruments. We are named for the late Professor Armand DeLong, a leader in the field of electron optics. Founded in 1962 and headquartered in Brno, Czech Republic, we have since built a long history and strong reputation for developing and producing electron optical components, along with benchtop and compact transmission low voltage electron microscopes, namely the benchtop LVM5 and compact LVM25. Without any further ado, I'll pass over control to our presenter, Dr. McCuskey.
Thanks, Jared. Appreciate the opportunity to present here, and appreciate everyone for taking the time to join today. I just wanted to share a little bit of background. I've had over 15 years of experience as a scientist in academia, national labs, corporations, and startups. I've been lucky enough to publish a few papers and really have a passion for helping make the world a better place through education, health, and the environment, and doing leadership coaching at the intersection of science and business. And so really excited to be presenting some of the exciting science in these areas. I also wanted to share there's a lot of great resources that go deeper than I will have time to cover in the presentation today. You can find them on the DeLong website. There's a lot of great profiles of users and their particular applications. There's a lot of comparisons of the techniques and application notes. So I really want to encourage everyone to look into those resources of interest for them after the presentation. So to briefly outline what I hope to cover today, obviously the first section will be covering microplastics and nanoplastics, then an overview about carbon nanotubes, and then going into 2D materials and talking a little bit about some of the research in these areas and how characterization plays a really key role in each of these areas of research and these interesting materials. Along the way, we'll be kind of talking about the different techniques and a survey of what's available. And we'll go into a deep dive, especially on the LVEM technique as we go through this and show its strengths for advancing research in these spaces. So to kick things off, we'll start with the area of microplastics and nanoplastics. And just to kind of get a sense of familiarity with everyone in the audience today, I'd like to just do a quick poll about what your level of familiarity is with various microplastics and nanoplastics, just kind of what you feel like your level is.
So the poll will be open for another few seconds while we collect as many results as possible. So the results say that the majority of people are somewhat knowledgeable, and the next equal tie is just learning.
Wonderful, wonderful. So we've got a range of experience in the audience today, which is great. So I'll try to speak to all of these levels as best as we can going through. Okay. So let's see here. So to kind of start out with a little bit of a high-level overview about why microplastics and nanoplastics are of interest, I found some interesting quotes in the literature. It really kind of struck me, but researchers know almost nothing about nanoplastics. They are invisible and cannot simply be scooped up. Just measuring them has stumped scientists. researchers still can't agree on whether pollutant-carrying microplastics are a significant problem, says Jennifer Lynch, a marine biologist affiliated with the U.S. National Institute of Standards and Technology in Gaithersburg, Maryland. Not enough information is available to fully understand the implications of microplastics for human health. However, effects may potentially be due to their physical properties, size, shape, and length, their chemical properties, the presence of additives and polymer type, their concentration, or microbial biofilm growth. And so there's a call in the literature that is really talking about, there's not enough information yet known, which is always a great opportunity for researchers to go and try to solve these problems and fill these knowledge gaps. I think we all have a strong intuition that it's generally not a great thing to have a lot of microplastics and nanoplastics in the environment. But I do think that there is a lot that we can still learn. And so obviously, when we talk about microplastics and nanoplastics, the size is inherent to the name of these materials with the micro and the nano prefix. And so it's important to kind of get a sense of the size range and the scale range that we're looking at. And so, this chart kind of gives a sense of scale of relative biological objects, with fish eggs and larvae being from about 100 microns to a millimeter in size, roughly. Looking at human macrophages as being between 10 and 100 microns, and getting a sense of these various organisms and their size. And then looking at maybe some non-biological particles such as sand and sediment, which might range from a millimeter down to 10 microns, or asbestos flakes, which might be from 10 microns down to 100 nanometers. Obviously PM 2.5 and PM 10 spans those ranges that are defined by their 10 micron and 2.5 micron or smaller diameters in their name. And so these are all various senses of particles that are in the environment that we might be familiar with. And so as we begin to think about particles that may be able to cross the blood-brain barrier, especially those smaller than 2 nanometers, but research suggests maybe in some cases even larger. Larger nanoparticles may be able to cross into cells. It's interesting to kind of understand what are the tools that we can use to measure objects at these different length scales. So obviously, if it's greater than 1 millimeter, we can see them with the naked eye, but if it's greater than 100 microns, we could use an optical microscope. But we might need to use other types of microscopies as we get into these smaller microplastics and nanoplastic regimes. And so the morphology is really critical to inform the nanotoxicology risk assessments. There's a lot of literature that shows just in general the shape and the size and the charge and the surface coating and the composition and the morphology of nanoparticles all play a role in understanding what hazard may be present for different compartments of the environment, different types of cells. And so it's important to really thoroughly characterize the materials of interest in order to understand what the risks are. And looking at the nanotoxicology literature is a great guide. Some general trends that have emerged are that smaller particle sizes in general can increase toxicity and cellular uptake. Being smaller and more mobile and easier to penetrate some of these natural biological barriers can increase their ability to be taken up by the cells. The reactivity also can change as a function of the increased surface area in some cases. The surface charge is important as well. In general, it looks like positively charged nanomaterials tend to be more toxic due to increased interactions. But if it's negatively charged or encapsulated with a neutral charge on that surface coating, it's important to understand what role that might play, especially as it might absorb other materials as it navigates through the environment. The surface coatings will dictate cellular responses, and again, what might absorb or desorb as these materials move through the environment. But there's really still no clear correlations. There's some case-by-case information, but in general, you really have to look at the role of the surface coating to understand what that might play. Of course, the composition of the material itself, maybe it's a different type of plastic, maybe it's a composite plastic, that might be able to release some metals. Those will impact the various rates of toxicity if there's release of ions. And of course, the morphology is important. There is literature that shows rod and fiber-shaped, fiber-like materials can be taken up less efficiently, but can induce stronger damage to cells. And so, again, it's really important to characterize these materials thoroughly. And so it's really important with the micro and nanoplastics space, because there's a range of types of shapes and sizes and morphologies as these materials degrade as they move throughout the environment over time. And so there's been a lot of effort. Julien Gigaud's group in France has been really leading the way, trying to create some standard materials and some kind of well-characterized reference library materials, if you will, to really make these studies more cross-comparable across labs as we look at these potential impacts. And so in this particular case, they were looking at plastic debris that was collected on a beach in France in September of 2018, and their go-to technique for characterizing the material was transmission electron microscopy. It provides a great way to get the size and the size distribution and the morphology all in one single sample preparation, all in one single measurement. And it also allows the ability to survey for a large number of particles across the grid. And so just a quick recap of the technique of transmission electron microscopy that may be familiar for many people in the audience. You can kind of think of it as you have a light source illuminating a sample and how much light is passing through onto the film or the detector at the bottom. And so in this case, though, rather than using a visible light and lenses and apertures like a photographic camera might, it's using an electron gun to create an electron beam. And so it's a much shorter wavelength of light. You still have some apertures and lenses to focus that beam onto the sample. The electron beam will then pass through the sample, the transmission element of the name. And as it passes through some additional lenses and apertures to focus that beam onto either a phosphor screen or the film or the CCD detectors, you end up with a final image projected there so that you can see what the sample contains. And so this beam path is under a high vacuum, which is critical for the success of the technique in order to allow it to function correctly. And there's an important kind of concept with the theoretical maximum resolution of a light microscope. And if we think about the visible wavelengths of light for optical microscopes, it's limited by the wavelength. And so with the de Broglie principle and electrons behaving both as waves as particles, you can have the wavelength of a beam of electrons being related to their kinetic energy. And so you can actually begin to, if you have a higher energy, have a shorter wavelength. And so that manifests itself when you have an electron beam source that's typically either tungsten or lab 6 crystals for most TEMs. As you apply increasingly high voltages, you get increasingly shorter wavelengths of these electron beams. And so for your theoretical maximums, you can actually get down to much smaller than the dimensions of the atoms of the materials that you're looking at. And so even when you get to a 5 kV or 5,000 volt accelerating voltage, you can get a wavelength of the electron beams being about 0.017 nanometers. And so again, the beams need to be under high vacuum, because if the electrons do interact with any atoms or any molecules, they will interact and not make it to the detector. And so you basically would be, for the visible equivalent, kind of looking through a fog on a cloudy day and not able to see very far down the beam path and not be able to see your sample of interest. And so the other key difference between the optical microscopes is the magnetic lenses that are used instead of the actual physical optical lenses. The magnetic fields cause the electrons to move according to the left-hand rule, and so you can do your you're focusing of the beams without them having to physically pass through a lens. And so these are some of the important concepts for transmission electron microscopy and what gives it its strengths for looking at these very small materials. So the conventional transmission electron microscopy that's been around for many decades, the Nobel Prize winning technique, it often operates around 100 kV for routine imaging. There's an example here of a reference material from the National Institute of Standards and Technology. This one happens to be a silver nanoparticle reference material. They imaged it with a conventional transmission electron microscope to show the representative size of the particles. It really is a go-to gold standard technique for size characterization of nanomaterials. So as you go into some of the higher accelerating voltages, the higher resolution transmission electron microscopy, or HRTEM, you can begin to see the atomic lattice spacing of materials, and it allows you to get good, useful information about the crystal structure of the materials, about grain boundaries and transitions between the different crystal domains of the materials. And so it can become a very useful technique. You can get some understanding of the materials from that lattice spacing. And with the low voltage, you begin to have the advantage of an increased contrast for carbon-based materials and low Z elements in general. In this particular image, it shows an example of nanocellulose with a much higher contrast with the low voltage electron microscope. Typically, you may only see very faint grays with a conventional TEM, but with LVEM, you get much greater improved contrast. We'll talk about that more as we go through the presentation today. The main reason for this low voltage concept, again, it increases the image contrast of these low atomic number materials. And it also allows for the use of permanent magnetic lenses instead of electromagnetic lenses. And this allows the column of the transmission electron microscope to be miniaturized for the low voltage EM. And we'll talk about those advantages a little bit more as we go through as well. So this graph, it's a great way to kind of understand how the increased image contrast really works by giving a different amount of interacting electrons for the various places in the specimen. And so the amount of interacting electrons is given also by the atomic number of the specimen matter in the way that the number of interactions will grow with a growing atomic number. And so this is the main reason why specimens for the standard, kind of conventional 100 kV microscopy are stained with heavy metals to get sufficient contrast for low Z materials. And so you have to manipulate those samples to kind of get some of the edges to show a little bit crisper contrast than you can get with the actual low Z elements. And so the advantage of the low energy is that you don't have to do any of this staining with the heavy metals. You can see them closer to their native state. And the degree of the scattering is represented by the scattering cross-section quantity. And you can see that for the cross-section for the electron scattering on the y-axis will increase as you decrease the accelerating voltage. And then you can also see that as the atomic number of the material increases, you will get a increasing cross-section for the electron scattering as well as you go across and increase the atomic number. So you can actually get, with a low accelerating voltage, a higher contrast of these low Z materials than you can at a conventional or high-res TEM with some of the heavier materials. So it's a very interesting phenomenon feature that is opened up by this low accelerating voltage. So this slide shows some example images of an unstained low voltage electron microscope image versus a heavy metal stained conventional TEM image, and you can begin to get a sense of the increased contrast that is afforded by what we've been talking about here. In this particular case, it was a biological specimen, a particular microorganism, and the advantage again is they can be imaged directly without having to do those heavy metal stains. and there's no artifact structures on the edges of the material. So it gives you a much more direct idea about surface roughness, about surface area, and about the size of the materials, which again correlates back to the hazard and the risk analysis for these materials in the environment, as we looked at that earlier. So there's currently 2 LVEMs on the market, the LVEM5. It's a benchtop electron microscope introduced in 2003. You can think of it as an entry-level system. It's got 3 imaging modes of TEM, SEM, and STEM with as resolution as small as 1.2 nanometers. And it's very commonly used for nanomaterials analysis and in-lab electron microscopy. As you can see, it has a very low footprint. It can sit right on the benchtop with the equipment that supports it right underneath the table. And it is driven by a standard computer and an interface controller. For the LVEM25, it can go up to a 25 kV accelerating voltage in its TEM mode and has resolution to 1.0 nanometers. Introduced in 2014, it's currently the most powerful low voltage electron microscope on the market. And it also offers STEM mode with resolution down to 1 nanometer as well. This is often used in hospital imaging labs where they, or in core facilities where they don't want to have the space and infrastructure of a conventional TEM. It has a much smaller footprint and lower operating cost. And it also allows the increased contrast for carbon-based materials and for thin sections. So these practical advantages of the low footprint, it's also been optimized for the ease of instrument use in the day-to-day operation, and no special facilities being required, all lead to much lower operating costs and much lower initial capital outlays for installing this type of equipment. And the other advantage is that it serves 3 microscope modes in one, with the TEM, SEM, and STEM all in one instrument with that low footprint. So in keeping with moving on through the different topics, we'll move on to the carbon nanotube section. And for this, I'd like to open it up for another poll question, and just kind of get a sense in the audience of, how often would you like to be able to analyze samples with a low atomic weight or organic materials? If you had unrestricted access to an instrument, this might be a little bit of a imaginative scenario, a wish list case, if you will. But just trying to get a sense of, if it could meet your needs anytime, anywhere, you don't have to wait 2 or 3 weeks at the core facility, what might that look like? All right. All right. Thank you, Jared, for running the poll there. And it looks like we have folks ranging from occasionally a few samples a year to most folks would run a few samples a month. And several people would run a few samples a week very frequently. And so, yeah, that would be something that would be very useful then to have that additional access to the instrumentation, having it right there in the lab. I know when I was working in the lab, for me, it would have been routinely because there was a large volume of materials that we had to characterize. So wonderful. Appreciate everyone's participation in that. And for carbon nanotubes, they're really interesting. Obviously, they could benefit from frequent characterization, but they have a lot of applications in different industry spaces. Carbon nanotubes have been used to make tennis rackets lighter and stronger. They've been used in bicycle frames and yachting masts, wind turbine blades. They've been made in bulletproof vests. There's a lot of ongoing sensor research, a whole variety of other applications, too much to fit on a single slide. And really what's driving a lot of the interest in these materials is the material properties of the increased strength to weight ratios, and the conductivity enhancements that carbon nanotubes can afford to composite materials. So it's a really wide range of applications with these materials. Looking at the different characterization tools that people often employ to study carbon nanotubes, it includes electron microscopy, of course, with TEM or SEM or LVEM. Folks also use atomic force microscopy, Raman spectroscopy, XPS or X-ray photoelectron spectroscopy, a wide variety of techniques in order to understand and characterize these materials. Some of the properties that are of interest, of course, are the diameter, their length, correspondingly the aspect ratio, the degree of dispersion of the materials of the tubes, if they might be single wall versus multi-wall, and also understanding about their chirality. Again, TEM is kind of one of the gold standard techniques for characterizing the size and the diameter and the morphology of these materials. This is an example from a publication about their characterization that you can see it provides with conventional TEM, some images about their morphology and degree of dispersion. And more recently, studies showing with LVEM, with carbon nanotubes. Here you can get a sense of that increased contrast in carbon nanotube samples. Again, this is especially important for researchers in the environmental space as they're looking at any potential new hazards and risks of these new material properties. And so obviously, the National Institute of Standards and Technologies got interested in creating reference materials for carbon nanotubes and successfully created these to a great technical accomplishment and a great boon for industry, making these standard reference materials. And so one of the key aspects then is to understand how to prepare these samples for TEM analysis and to study the dispersion of these materials. And so in a recent study, NIST looked at various methods of preparing carbon nanotube materials for TEM and found some really informative and instructive results in their presentation. So they looked at ranges of solvents and dispersion methods from chloroform, which they found to be the preferred method, yielding some isolated tubes and clean ropes, and giving the most representative look of the material. They also looked at some various surfactant methods, at DNA suspensions, at toluene and phosphatidylcholine, and sodium dodecyl sulfate to look at these. And so we'll go ahead and look at some of these. And, excuse me. And so as you can see in the chloroform images, the carbon nanotubes were deposited in an area with various ropes, and single nanotubes were dispersed as well with one another. And it showed that it was a very good way to provide images of those single nanotubes as they're bound into ropes and single nanotubes. These particular nanotubes are on the order of 0.7 to 0.8 nanometers in diameter. And these images in this publication were with a conventional TEM. So as you can imagine, a low voltage EM will give you an even greater degree of contrast than these images. And so then looking at the chloroform prep, you can see in some of the ropes, you can see the carbon nanotubes with the little circles at the ends of the individual nanotubes projecting out from the rope structure. So it's a very nice preparation method to get some good images. When they looked at the sodium deoxycholate method, the ropes and carbon nanotubes in a length sorted fraction were deposited, and you can see that it also provides very nice uniform images. So this was another approach and technique that was quite suitable for getting good high quality images. As they looked at a DNA method where they used DNA to isolate the single wall carbon nanotubes, there were some ropes and some single tubes present. In this particular image, the length of the nanotubes is approximately 300 nanometers across this particular gap in the structure where they're obtaining the images. And when they obtained a high magnification image of the DNA single-wall carbon nanotube ropes, the arrows can show the, in this particular image, where the individual nanotubes are, and then you can also see the DNA kind of draping around these carbon nanotube ropes as well, so kind of encapsulating the bundle of tubes into that rope structure. Looking at some of the other techniques, the phosphatidylcholine was a low magnification image presented here of the carbon nanotube ropes, and you can see a lot of associated lipid vesicles. And so this was not quite as effective of a sample preparation as some of the other approaches studied. And so again, their conclusion was that the chloroform preparation is the preferred method. It yields some isolated tubes and some clean ropes and provides the most representative look of the material. And to me, the most important aspect of this is its transferable knowledge between both low voltage electron microscopy and transmission electron microscopy, as they both use the same sample prep techniques. And the LVEM can provide, again, the enhanced contrast of these materials. So with that transferable knowledge and the enhanced contrast, it also leads to some great ease of use for the LVEM, with the advantage of knowing the best sample preps and then having an instrument that allows for more trained users and more rapid data collection. It can allow for faster research progress in order to understand the materials both before and after any particular transformations may be done or any manipulations are done as you're studying the material properties of the carbon nanotubes. So let's move into the section on graphene and 2D materials. And as we kick this section off, I'd like to do a final poll just to try to understand in the audience, what are the challenges that you encounter when characterizing 2D materials? Is it contrast or resolution or stability? What are the biggest challenges?
So we'll open the poll for a few moments here just to give people the opportunity to give their responses.
Okay, it looks like resolution is the biggest challenge, and then contrast and stability also are important challenges as well. Okay, appreciate everyone participating in that. And so there's a wide range of two-dimensional materials that are of interest in the literature, ranging from graphene to graphene oxide to amexines or transition metal dicalcinides to bilayer materials, for example, like bilayer graphenes. So there's a wide range of interesting planar materials, 2D materials that are being studied. They have a wide array of areas of interest and applications, everything from aerospace to additive manufacturing. Antimicrobial face masks using graphene have been getting some media attention over the summer. Energy storage and generation, medical applications, polymers, again, sensors, touch screens, transparent electrodes, so a wide range of various application spaces for graphene. For The various characterization tools for 2D materials, again, a lot of familiar friends, if you will, in this space. Transmission electron microscopy is, again, a key characterization tool, along with the electron diffraction tool in TEM. Scanning probe microscopies are, again, used, Raman spectroscopy, X-ray diffraction, X-ray photoelectron spectroscopy, a wide range of various tools are used to characterize these materials. TEM, again, obviously has the advantage of images for the morphology, but it also includes some advantages with both conventional and low voltage. Comparing their advantages, the conventional systems will have more availability of legacy systems. They can offer some higher magnifications, and some of the multi-million-dollar latest generation systems can also offer elemental mapping, such as EELS or EDS capabilities, and they can also do selected area electron diffraction. While the low voltage TEM systems, they offer the increased contrast for the low Z materials. They also offer the high magnifications, and they have the advantage of a compact laboratory footprint, the ease of use and maintenance with the lower operating costs that are enjoyed with that. And they also can do the selected area electron diffraction, which is a very helpful tool with 2D materials. TEM is really great for visualizing planar materials. If you can prepare the samples such that you have the plane of the material supported as a film, there's very thin sections of material that is the electron beam is transmitting through, and so you can get in some cases information about the hexagonal lattices of these materials. And it also allows you to discriminate the multiple layers. If you have bilayers of graphene and if there's different stacking sequences, it's possible at very low accelerating voltages to understand more about these materials. So with low voltage electron diffraction, the electrons pass through the sample. They are then scattered by the elements in the sample. The objective lens will then collect electrons that are scattered from one point of the sample into one point on the detector. And it's important to note that at the dashed line in this particular figure, the electrons scattered in the same direction by the sample are collected back into a single point, and that this back focal plane of the microscope is where the diffraction pattern is formed. And so in this particular example from the Piazza group this year, they were able to discriminate bilayer graphene with different stacking sequences using a very low accelerating voltage. Again, this unique feature is enabled by the LVEM5, and you can see with the selected area electron diffraction images, they're able to understand a AA versus a AB bilayer stacking structure, and also begin to understand information about multiple domains in the stacking structures. And it also allowed them to study about different patterns for specimen flakes after exposure to a hot filament promoted hydrogenation process, and begin to understand what changes to the structure of the material were taking place as a result of the chemistry in these processes. And they found that genuine diamine can be produced by chemisorption of the hydrogen atoms to the top and the bottom surfaces of the bilayer graphene or the two-layer graphene. And that the subsequent interlayer bonding between the sp3 bonded carbon atoms, if the stacking sequence was pristine, was either a AA or AB pattern, depending on their process. And so all of this, again, is enabled by the electron microscopy and is performed with the low voltage electron microscopy in the selected area electron diffraction. So the increased contrast of the low Z materials is obviously an advantage for the low accelerating voltage. The electron diffraction enables the determination of the lattice information as well as the stacking patterns in the bilayer materials. And the ease of operation with a small laboratory footprint enables a rapid and a high throughput analysis, which is critical for the structured property relationship studies that are really advancing the types of materials that are available for study and understanding their properties. So to wrap it up with some brief conclusions, the LVEM is a powerful tool in the study of nanoplastics and microplastics. It's also a powerful tool in the study of carbon nanotubes, as well as for 2D materials and graphene. We've seen how in each of these material cases, the role of electron microscopy, in particular electron microscopy with low accelerating voltages, provides increased contrast. It provides critical information about the morphology, the size, the shape, the surface area, and even information about the composition and the structure of these materials. And we've also learned that a lot of the sample preparation techniques are transferable knowledge across the TEM domain. So there are some references available upon request, and again, also some resources available on the lv-em.com website. There's a lot of great resources there as well. I really encourage everyone to check it out, and thank everyone for your time and attention today. And I'd like to open it up for any questions that you have.
So if there are any questions, feel free to use the Q&A button at the bottom of the Zoom panel and ask. We'll be happy to address as many as possible. Rob, so far there aren't any questions from that came up during the presentation. So we'll see. We'll give attendees maybe a minute or so to see if they maybe have some questions, and we can address them as they come in.
Wonderful.
Doesn't look like we're getting any questions today. If anybody does have any questions later on, please feel free to write in. There will be information that you can use to reach either myself or Rob to address your questions. I'd like to take this time. Oh, wait, we have a question coming in real quick. The question is, what's the best way to measure and prepare bacterias? Rob, do you want to take a quick moment to answer that question? A couple of techniques. I know it's a little outside of the presentation scope.
Yeah, but it is a great and interesting question. It really is with the biological space. You know, if you're looking at a bacterial cell and you just want to get a sense of the overall cell morphology, then folks may you know, just deposit the bacterial cells directly onto a film. But typically, I'm more familiar with researchers that are interested in understanding where the nanomaterials of interest went into cells, and so they might do some casting of the cells into, say, a polymer and do some microtoming, and then image those thin sections. You know, the types of grids in that case, you know, you could use whatever mesh you feel would be appropriate to support the thickness of your particular films that you're looking at. But pretty much any of the standard meshes that are available are suitable for the technique. And so sometimes it comes down to personal preference. Sometimes it comes down to having a smaller area. So maybe a higher mesh number to have less breakage in those films. So it's kind of a little bit of personal preference there sometimes, sometimes depending on the sample.
Thanks, Rob. We have two more questions to address. One would be, what could be the best method for deposition on nanoplastics on metal grids?
Right, on metal grids, so I'm assuming this is like a metal grid with a polymer support film on it, as opposed to just an empty metal grid. You know, typically, you know, I'm familiar with folks that are using, you know, a thin support film. In general, you would like to have a thinner support film, as thin as possible, when you're going to deposit the nanoparticles onto the metal grid. I have seen evaporative techniques. People might just take a droplet of the material and allow it to evaporate on the grid. That can lead to drop pinning, or the so-called coffee ring effect, where you can get a lot of the nanoparticles deposited on the edge of where that droplet is drying. And so you get kind of a ring with a high concentration of aggregated particles and a much lower deposition in the middle of where the droplet was. In other cases, I've seen people float a grid on top of a droplet if there's some kind of interaction between the film and the particle that would allow them to deposit. Maybe there's an electrostatic interaction, for example, that might drive deposition. That could be another approach as well. So those are some of the approaches that people do. There's also the Nanotechnology Characterization Laboratory, which is part of the National Cancer Institute and NIST and the FDA. They have made a Say Cascade Protocol series, and they have some protocols there for deposition of nanomaterials onto TEM grids for sample preps. And so that's also a great resource if you're looking for more information.
We have two more questions, Rob. Both are specifically related to LVEM, so I think I'll address them directly. One question is about the type of grids to use with LVEM, which is somewhat dependent on the specific applications. For the materials we were talking about today during the presentation, so nanoparticulate materials, we typically recommend ultra thin carbon film grids. So these would be metal grids. It doesn't specifically matter if it's copper or nickel, for example, with a thin film of carbon, typically on the range of 3 to 15 nanometers in size. The thinner, the better for optimum results at low voltage. The only reason you would use slightly thicker films would be for the additional strength for larger nanoparticles. So anything in the ranges of 20 nanometers and larger. And what's important is that we don't typically recommend the use of polymer support films, as the low voltage capabilities of the instruments add background contrast that would come from the polymer. So basically it's thin carbon films that are recommended. And the second question was, what was the maximum thickness of the electron transparent medium in LVTEM? So I understand from the question is what would be the maximum transmittance or the maximum thickness for electron transmittance under low voltage, and it really depends on which LVEM you're using. So the benchtop instrument, which operates at 5 kV, the maximum thickness for carbon-based material for maximum resolution is 20 nanometers, whereas for the LVM25, which operates at 25 kV, the maximum thickness for carbon-based material is typically 80 to 100 nanometers of thickness. Now, that really can be further enhanced by using the scanning transmission modes in either systems. So the 5 kV scanning transmission could be 65 nanometers, whereas for the 25 kV instrument, the maximum transmittance for carbon-based materials would be closer to 200 nanometers. And Rob, I think that's all the questions that we have for today. So I think we'll close the Q&A there. I'd like to thank you, Rob, for the informative presentation, and thanks again for being with us today. I'd also like to thank all of the attendees for being with us. You're going to be presented with a short survey after you sign off, and we appreciate if you would take the time to complete the presentation, the survey. That would be much appreciated. For your information, we'll be posting this webinar for your review in the near future on our website at www.lv-em.com. If you have any further questions, please feel free to reach out directly to either Dr. McCusby or myself. You'll be receiving an email with contact details later on. So again, thank you very much, and have a good evening or afternoon, depending on where you are.